Experimentalists do not deal usually with probabilities or amplitude of probabilities. So what they measure when they look at the collision between particles is a cross-section. So for instance, if we consider a collision of two particles, A and B, with four momenta P1 and P2, and leading to a bunch of particles, C, D, etc., the general expression for the differential cross-section associated with this process is V1 and V2 are the velocity vectors of the incoming particles as viewed from the laboratory frame, and E1 and E2 are their energies. And we say that this term accounts for the kinematics in the entrance channel. We then have the modulus squared of the amplitude of probability for this collision to occur, and which we calculate with Feynman diagrams. So that gives us a probability for this collision. And this is a dynamical term. And finally, we have the Lorentz invariant phase space, accounting for the kinematics in the exit channel. This is called the Lorentz invariant phase space because if we integrate over all the momenta, we get a Lorentz invariant scalar. Indeed, as usual, the integral over just the space-like component of the four momentum is not a Lorentz scalar, but once we divide by the energy, that is a Lorentz scalar. Term just account for energy momentum conservation. We see that we have three integral per particle, so 3n minus 6 integral in total, and therefore we can use this equation to define a differential cross-section. The minus 6 comes from the fact that we start from j equals 3, as we noted j equal 1 and j equal 2 for the incoming particles, so we already have the differentiation with respect to the outgoing particles. So this differential cross-section gives us something proportional to the probability for the collision to occur and to produce a set of final particles, C, D, etc., with the final momenta, P3, P4, etc., at 2 p.m. But if we don't care about this final momenta and we just want to have something proportional to the probability for this collision to occur, whatever the final momenta, then we can integrate over this final momenta, and in order to get a total cross-section, which will have the dimension of an area. We can similarly define decay rates to describe the probability for a particle to decay into a subset of particles per unit of time. This is used to quantify the probability for the decay of a particle into a subset of other particles. We usually consider the particle at rest, and that gives us the decay rate in the proper frame of the particle. If we want to evaluate this decay rate for a moving particle, we just need to boost, and in terms of lifetime, that gives us just the usual time dilation of special relativity. We recognize in the expression for the decay rate the modulus square of the amplitude of probability. We also have the Lorentz invariant phase space. However, now the final state starts with j equal 2. And we have a kinematic factor for the entrance channel, which in this case is very simple because we only have one particle and it is at rest, so the energy is m1. As for the cross-section, we can integrate over the final state in order to get a total decay rate for this specific channel. And if we were to sum over all the possible channels, that means the particle A can decay into B, C, etc., but it can also have some other possible decays. And considering all that together, taking the inverse, we will get the lifetime of the particle.